Hello, this is Sergio Cicero from University of Cantabria, and I'm going to present the work entitled Effect of Graphene on the fracture behavior of 3D printed PLA single-edge notch bending specimens, a work that has been done in collaboration with my colleagues Víctor Martínez and Borja Arroyo. The contents of the presentation are divided in 4 sections. First of all, an introduction and explaining the reason for this research, then materials and methods, results and discussion, and finally the main conclusions behind this research. Well, additive manufacturing is a booming field with a lot of research efforts, a lot of industrial interest because it allows obtaining complex geometries that may be generated easily. It is mainly used to obtain prototypes, and as we'll see in a while, its application on high demanding structural components is still limited. In this technology, the wire material, and we are talking about fused deposition modeling, the wire material is deposited layer by layer. The obtained materials have lower resistance in terms of tensile and fracture properties than traditional processes, and that's why I was mentioning before that it is very difficult to generate 3D printed materials with high performance in terms of mechanical properties. There is, in any case, a strong influence of the printing parameters on the resulting material properties, and there are also a number of printing parameters. And additionally, concerning the fracture behavior, there is a clear lack of knowledge. So there is room yet to develop research on this field. With all this, what we are trying to do in this work is to characterize the fracture behavior of a particular 3D printed material. So we will test the primary polymer obtained by 3D printing, PLA, and also the resulting composite of adding graphene to PLA with a fixed amount of graphene at 1% in weight percentage. So graphene is used as the reinforcement here with 3 different raster orientations when printed: 090, 30 minus 60, and 45 minus 45. You may see the printing strategies on the figure on the bottom part of the slide. We completed tensile tests as explained on the paper and fracture test, following in both cases the corresponding testing standard, ASTM. You may see the corresponding geometries on the figure, and also we completed the research with the scanning electron microscopy analysis of the fracture surfaces in order to relate the macroscopic observations with what is happening on the fracture surface, being the area below the load displacement curve, and the rest of the parameters being geometrical. That was observed here. If we add graphene, the curves goes leftwards and upwards, increasing the resistance parameters and decreasing the Concerning the fracture results, here you may see what we obtain, and it is pretty interesting because the addition of graphene on the fracture properties and its effect strongly depends on the raster orientation. Particularly for raster orientation 090, there is very little effect or negligible effect. However, as long as we change the raster orientations, for the other extreme condition, 45 minus 45, the addition of graphene provides a high enhancement of the fractal properties, with the 30 minus 60 raster orientation having also an increase in the fractal properties, but this increase being much more moderate. We made also, as mentioned before, a SEM analysis, and these explain the previous results quite straightforwardly. When we analyze the materials, the 45 minus 45 material, which are these figures below, we may observe that there is a change on the fractal mechanisms from these brittle ones to this other more, let's say, non-linear, a much more rough surface in all the filaments for the 45 and the minus 45 filaments. However, if we focus our attention on these two images here, this corresponds to the 090 raster orientation of pure PLA, which is brittle, and this corresponds to the 090 raster orientation with a 1% of graphene. It may be observed that there is a change of fractal mechanisms just in one half of the ligaments, those corresponding to a particular orientation, with the other orientation having still brittle mechanisms. So in 45 minus 45 raster orientation, there is a full change of fractal mechanisms, whereas for the 090, the change in fractal mechanisms is much more partial, with little effect on the overall macroscopic behavior. The conclusions, the main conclusions are the addition of graphene generates an enhancement in the tensile properties, this enhancement being dependent on the raster orientation. For example, we saw that the tensile properties had a larger change in the case of 45 minus 45 raster orientation. This same raster orientation presents the lowest values of fractal toughness when working with pure PLA, but this changes completely when adding graphene, with 45 minus 45 raster orientation presenting the highest values of fractal toughness when adding the 1% weight of graphene. Raster orientation 090 does not show any kind of improvement in fractal toughness, and on the contrary, this fractal resistance evolution show a clear evolution, a clear increase in the 30 minus 60 and especially 45 minus 45 raster orientations. And all these observations have been justified by the evolution of the fractal micromechanisms observed in the scanning electron microscope. So that's all. Thank you very much for your attention, and if you have any questions, it will be a pleasure trying to answer them. Bye bye, ciao.